Hello, in this video we're going to look at cosets in another group, a dihedral group. And now we're actually going to look at right cosets as well, so we can see some of the differences between the two, and that sometimes left cosets and right cosets are the same, and sometimes they're slightly different. Let's look at another example of a coset calculation. Let's let G be the dihedral group with a hexagon. There's a particular reason I'm picking such a large group. I'm sorry it's going to make some of the calculations hard, but it turns out you need to pick a large enough group to get one of the bad counterexamples I need to show. So sorry that the calculations are going to be a little complicated. The good news is that this means the calculations I'm going to ask you to do are going to be significantly easier. So this is going to be my larger group. My subgroup is going to be the cyclic subgroup generated by the square of the rotation. So remember, the rotation in this case would be the rotation of order 6. So just a 60-degree rotation. So squaring it is a 100-degree rotation. So when you do a 120-degree rotation, 0 goes to 2, 2 goes to 4, and 4 goes back to 0. And likewise, 1 goes to 3, 3 goes to 5, and 5 goes back to 1. And so there's the cycle decomposition for that permutation. But H is the cyclic subgroup generated by this permutation. So H consists of the identity element, this permutation, and all powers of that permutation. If you square that permutation, you'll see that 0 goes to 4, goes to 2, and 1 goes to 5, goes to 3. And this element has order 3, this element has order 3, these cycles commute, and so this product has order 3, and so we see that if I cube this element, I get the identity. So this is the entire subgroup. The subgroup itself is order 3. So that's all of H. Note where the commas are here. This is a product of 2 3 cycles. And these are 2 different elements here. Each element has 2 3 cycles, is a product of 2 3 cycles. So there are 3 elements overall. And each element is a permutation of 6 symbols. I state that because sometimes one can get lost looking at the notation, and sometimes students can make mistakes and put commas when there shouldn't be. So if I put a comma between 2 3 cycles here, that would indicate that these are 2 separate permutations, and that would be wrong. So this is my subgroup. All right, so now I want to figure out some of the cosets. Well, one natural coset you could look at is R times H. Here we should note what R is. It is the 6th cycle. And the other main element in the dihedral group is S, which is the reflection. One of the reflections. It's going to send 0 to itself. It's going to swap 1 with 5, 2 with 4, and it's going to fix 3. Why do I know this? Because remember, the way I think of these things is that it sends I to n minus I mod n. So let's look at R times H. Well, then you're going to get R, which is the full cycle. You're going to get R times R squared, which I'm going to call R cubed for a moment, and R to the 5th. So to make our lives easier, maybe I'm going to write it in the notation of powers of R for right now, and see if that might help. sometimes it's easier to write things down as permutations, and sometimes it's easier to write it in terms of powers of R and S. So there's one coset. What's another coset? Well, we can multiply by S as well. That would give us S, SR squared, and SR to the fourth. And naturally, you could also multiply by SR times H. Why would you want to do that? Well, looks like I'm looking at elements of the form S times powers of R here, and one I don't see yet is SR. In this coset, or that coset. So I know that it appears in some coset, so I can look at it being an element in this coset. So now I have 4 cosets. I can conclude these cosets are all distinct so far because each one has at least one element that appears in no other coset. For instance, these only have odd powers of R, and these 2 cosets don't have any S's in them. Likewise, these 2 cosets, this coset only has S times an even power of R, and this coset only has S times an odd power of R. So these 2 cosets are disjoint. And why are these cosets disjoint? Because these cosets have S times something. So we know these are reflections and these are rotations. So again, there's nothing in common. So these are distinct cosets. And there's 12 of them. So this represents all 12 elements separated into 4 distinct cosets. So all 12 elements of our group lie in 4 different cosets of H. Alright, so now I'm going to mention the notion of a right coset. So technically what I've been calling a coset is called a left coset. Although usually when we say the word coset, we always mean left. But there's also a notion of right coset, and that's of the form capital H times little g. And that's basically where you multiply by little g on the right. So it consists of elements of the form little h times little g as little h runs through all of the subgroup. It's a little hard to explain the motivation for this concept at this point. When I was talking about parallel lines, there we were always working with abelian groups. So for abelian groups, the distinction between left and right doesn't really matter because the multiplication operation is commutative. But when it's not commutative, you might actually get something different, as we will see. And this actually becomes a major point later in the course. So I have to mention it now. And so an example of a non-abelian group is the dihedral group. We'll let H be that subgroup we just talked about, R squared, the cyclic group generated by the square of the rotation. If I take the right coset with respect to R, then I still get R cubed, R to the 5th. That's still R times H. But I could see what happens if I look at H times S. And I get S, R squared S, R to the 4th times S. Contrast that with what I had for SH. SH was S, SR squared, SR to the 4th. Are these the same? At face value, it seems like the answer is no, because these don't look the same, but we need to keep track of the group operations. So RS is always equal to SR inverse. So, well, that should be a squared. So R squared S is SR to the negative 2, R has order 4 here, so that's SR to the 4th. So these two elements, R squared S and SR to the 4th, are actually equal. Likewise, it turns out SR squared and R4 to the S are also equal. So in this case, it turns out HS is equal to SH as sets. So in this case, this left coset is equal to this right coset. Similarly, you can look at HSR. R squared times SR, R to the 4th times SR. And let's see, what happens if I apply this relation? I get SR, SR to the negative 1, SR to the negative 3, but R has order 6, so that's SR, SR to the 5th, and SR cubed. And you can check that that was the same coset as we had earlier. So in this case, the left cosets and the right cosets are actually the same. But I do need to point out that this idea sometimes is false. Sometimes the left coset with respect to an element and the right coset with respect to an element are different. And the easiest counterexample would be a dihedral group for the larger group and the subgroup consisting of the identity and a reflection. And then the left coset would be the rotation, generated by a rotation. On one hand, you get R and RS for the left coset with respect to R, and the right coset with respect to R is RSR. Now we know SR is not equal to RS, because if that were true, then the dihedral group would be abelian, and it's not. Remember, the relationship is that you can move the rotation to the other side by inverting it. That's the way it works. So in this particular case, with respect to this subgroup in this group, this left coset is not equal to this right coset. So in general, there is actually a distinction between the two.